Guys, let us start with the continuation of our dynamics. As promised, we move to the conservation of momentum. Apologies for not showing my camera. That has been the recent problem. I promise in the next video, by the grace of God, I am going to be showing my face for you guys to see my face, because I love showing my face. You know that very well. Just because I think it is the best way for you to be able to see the way I am interpreting questions. It's another mode of learning. It is seeing the person that is actually doing the stuff, looking at the way he is thinking or going about the questions. So let us start. I am Engineer Oyedi, and this is Mostly Academy. For those that are just joining us, don't forget to subscribe and like our channel. We have a channel for physics, chemistry, and mathematics. For now, like I just said, the physics is what we are trying to upload all concept videos with respect to the syllabus, which we have been doing for quite some time now. It is a new channel. Like I told you, the old channel has been removed by YouTube. That is why we have to start over again. So, and I'm trying to do new videos and neglecting the old videos so that I will be able to go comprehensive or more detailed for those students that are in colleges and not in high school. So now here about conservation of momentum, we might have done that in our junior classes. We define momentum. Let's just start. Momentum is defined as simply as the product of mass and its velocity. So we can just recall that momentum is defined as the product of mass and its velocity. And because of that, we relate momentum. Basically, it is written as a capital letter M. So for now, I will write it as capital letter M. But basically, if you want to follow the physics way of interpretation symbol, we write momentum as P. It is a vector quantity. It is the product of mass and velocity. So always keep this at the back of your mind. Also recall from our laws of motion, we talk about Newton's second law of motion. We say Newton's second law of motion talks about rate of change, the law of rate of change of momentum. So that was the definition we gave to Newton's second law for those that started the dynamics concept with us. Now, I would say that momentum is a vector quantity. It is the product of mass and velocity. Now, students also need to keep it in mind that when we talk about momentum, we talk about another thing we call collisions. Now, collision, just for writing's sake, collision is just the subset. It's just a subset of linear momentum. That is when a body gains a momentum, it can collide with what? Another body. So collision and momentum, you can see what I'm saying. I'm always trying to explain by gesticulating. I'm doing that now. Apologies, you cannot see me, but at least you can hear my voice, which I think is the most important thing for now. So far, you can hear my voice. I don't think we have issues with respect to what we are doing. Sorry about that. Now, like I said, collision is just the subset of linear momentum. For every momentum change, or for bodies or two or more bodies in case of momentum, when body collides, there is now what we call the general law you've learned from class 9. I'm sorry, I'll be a little bit fast. That there is what they call laws of conservation of momentum, laws of conservation of momentum. I think it's just one law, so I should put law and not laws. So apologies for that. So law of conservation of momentum. So then you always keep that at the back of your mind, which I believe you have studied. So they say in a closed system or in a constraint, anyhow your teacher actually gave you the definition in junior classes, you can actually use any one. Does not change anything. It says what? Momentum before collision. That's just the word I want to write. Momentum before collision is equal to momentum after collision. So that is the definition of law of conservation of momentum. So students just need to keep it in mind that momentum is a vector quantity, and it's just defined as the rate of change of the product of mass and the change in what the velocity. Product of mass and velocity is called what momentum, which is a vector quantity. So, and we've also studied, remember that from our second law of motion, that the acceleration of a body, excuse me, I'm writing, acceleration of a body, acceleration is a vector quantity, is given as a sum of the force, that is the external force acting on the body, divided by the mass of the body. So that is F equals to ma, which we have also studied before. So all these things are what we are going to be putting in context to understand different cases of momentum. I believe every one of you have studied the definition of momentum in junior classes, which you define as the product of mass and velocity. The second law of motion talks about rate of change of momentum, which we have derived in the first in our introduction to dynamics and Newton's law of motion. So I said collision is a subset of what? Momentum. That is, when body gains momentum, they can collide with another body. That is why we call it a subset of what? Of linear momentum. And because of that, there's a particular law that holds for each and every one of them, that when body collides, their total momentum before collision is equal to total momentum after collision. So always keep it at the back of your mind. That it's very simple to know the acceleration of the body is always force of the body divided by the mass. So this will now lead us to what? Different cases of momentum, which is practically what I want to discuss about in this first slide. Talking about what we have learned before in junior classes and how to relate all those stuff that we have learned to understand some advanced concept which is going to be needed in numericals, and that is essence of what? Watching the concept video on Musti Academy. So we start with different cases of momentum. About cases of momentum, we take the first cases we call of gun. In class 9, that is SS1, you might have studied that when we talk about recoil of a gun, that is your application of Newton's law of motion, action and reaction are equal and opposite, or to every action, there's always an equal and opposite reaction. We can go by that by saying there is a gun, just for illustration straight. I am not drawing diagram to scale or anything, just for illustration's sake, please. I hope my students understand that. So don't laugh at my gun. So a gun was fired. A bullet was fired out of a gun. So we have the initial mass of the gun is capital letter M. So there's always something here that is going to be what? Pull, or what you pull it, right? So now you have the initial velocity of this one. You are pulling this one with a velocity of V. So bullet is now ejected from this. Bullet is having a mass of small letter M, and the velocity of what the bullet I take as what? As U. So according to law of conservation of momentum before collision must be equal to momentum after collision. This is what we are talking. Momentum before must always be equal to momentum after. So in that case, we say momentum is mass and velocity, already studied there. So we say the mass and velocity of the ball, like this, must be equal to the mass and velocity of the bullet. So directly we can say the velocity of the gun is equal to mu over capital letter M, which is basically most of the questions you solve for UTME, JAM, and also some other cases. Now, another case we can talk about is the case of, this is the first one, which I've discussed. The second one is a boy that is standing on a trolley. Another important one, because I have more than 12 years experience in teaching physics and mathematics, as well as chemistry. So I can tell you categorically what each exam is going to ask you, even without going to the exam or with you. You know, we solve those exams papers that have been released. We solve them for you guys to see how to get accurate answers and solutions to most of the questions. So in continuation to what we're saying, we are talking about different cases. We take the first case, which is the recoil of a gun. The second case I'm going to consider here is the case of a boy called trolley cases. Now, let's say there is a ground. We have a ground, and on top of the ground, we have a boy that is what? A trolley. Let's say we have a trolley. Just for understanding's sake, nothing more pretentious. And on top of the trolley, there is a boy. Now, the trolley is having a mass of, just like what I did at that time, the mass of capital letter M. So there's this case 2. I'm just giving you different cases which you can memorize formula. For those of you that you like memorizing formula. Now, there is a boy standing on top of this trolley. This is the boy on top of the trolley. So now this boy is standing on a trolley. The boy is having initial mass of small letter m. Then we say the speed of the boy. Now this boy wants to jump away from the what? From the trolley. Trolley is moving. You can see the mass of the boy is m. So the boy is moving with an initial speed of u. I will take that the speed of the boy, relative to the trolley, relative to trolley. So we say using conservation of momentum, just like what we've done in the previous one. So initial mass of the boy, we can say final mass of that. So always, please keep it in mind. You always use conservation of momentum. So that is what we use in solving almost all questions that we come across in momentum. So I don't expect us to have any issues with this one because it is one of the cheapest topic in physics, which I believe all of us do enjoy in our junior classes. Now we say the initial speed of the trolley, relative to the speed of trolley I didn't give you yet, should also be v. So what we are trying to say now is that at the speed of the boy relative to trolley will now be equal to initial before collision. You can say that is momentum before is mv must be equals to momentum after. This is where something m into bracket. The boy is jumping away. So we have to get the relative speed. So the relative speed will be the final, you can say the speed of the boy minus that of the trolley. That is the relative speed with respect to what? To the ground. The frame of reference here is the ground I am using. So now the boy is jumping away from a trolley. So far it is jumping away. So the relative velocity is u minus v. So keep this in mind, which is also very important formula you are going to come across in some cases whereby you have a boy jumping away from a trolley. So momentum before must always be equal to momentum after. So after the boy has jumped, the momentum after will now be relative speed between the trolley and the boy with respect to the ground frame will be u minus v. As we have talked about speed, relative velocity in the same direction and in opposite direction in our introduction to kinematics. So another case we talk about here is another very important one is the concept of impulse, which I think is always also very important. Now, in junior classes, we say change in momentum is called what? Impulse. Now, impulse we denote in physics by J, which is also a vector quantity. Let's keep that at the back of the line. So when momentum is initial momentum is m, the final momentum is mv, initial momentum is mu. So we say the change in momentum is now m into bracket v minus u, which is what you guys are used to in your junior classes. So the change in the momentum of the body is called the impulse. That means the amount of force that was impacted on the body, and the body has gained momentum. So the force that makes the body to be changing momentum with respect to the time. That is another definition we give to that. Remember from Newton's second law of motion that we say the second law of motion is called law of what? Rate of change of momentum. So from that, which we can actually recall, F equals to what? ma, or F equals, you can say m equals to what? A is a v minus u over t, which we call change in velocity over time. So what I'm trying to say here for understanding's sake is that from second law of motion, we know that F equals to m into bracket v minus u over t. For those that are just training us, it's just because I want to be a little bit fast here so that we can finish all what we have to do. So we can say F is equals to rate of change of m. So you say m dv, that's change in velocity over change in time dt. dv by dt. M dv is what we can say. M dv is momentum. So we say F equals to momentum, I say dp by what? By dt. I hope students can see that. And if you cannot see, please just let me know so that I can actually write it very well. I hope it is not cutting. So that is the way we come about rate of change of momentum from the second law. So what we are trying to say now, the change in momentum is now called impulse. So we now say dp from cross multiplication, dp, which is what we call impulse now, which we denote by j vector, is now equals to the product of force and what? The change in time. So what we all just want to keep in mind here is that the change in momentum, which you have studied from class 9, which we call impulse, which is noted by j vector, that is j is a symbol, is also equals to what? Force times what? Force times time. of force times change in time. So this is the method, or this is the simple formula you have studied before in your junior classes. So this formula, we are going to be using it because there are different cases in which we can also explain impulse. For example, in the situation whereby the force acting on the body is constant, we say the change in momentum, which we call impulse, is what? F times what? I said F times dt. Please, I have to put dt because the momentum is changing with respect to time, which is what you can say F dt, F times dt. So now, there are different cases. We can have a situation whereby the force is constant, which you need to know. Advanced students need to keep this in mind. And we can have a situation whereby the force is what? Is a variable force. Now, when the force is constant, it is just directly F dt. But when the force is changing, we now say we'll go with integration, which most students need to keep at the back of their mind. So when the force is what? When the force is not constant, we now say J vector, which is the impulse, is now equals to what? We have integration of F dt. We are taking the time from what? From time t1 to time t2. So guys, I'm sorry, I hope it is not cutting. So that is for variable force, when force is not constant. So because there are some questions in which we are going to be given a particular equation of a particular equation, which you are going to be asked to find the impulse of the body. So in that case, when the force is not changing, when the force is not the same, if the force is changing with respect to time, so we integrate to get the value of the impulse of that body. So always keep this at the back of your mind, because without this, you may not be able to solve some question. That is why I want to take you through the concept first before we start solving questions. So about what I'm trying to explain in essence is that impulse is change in momentum. When there is a change in momentum, you expect what? You expect what? You expect when there's a change in momentum, when there's a change in force, when the force is applied to a body, you expect a change in momentum. This particular change in momentum, when force is applied to a body, is called what? Impulse. So always keep that at the back of your mind. It is very, very important for you not to make mistake when dealing with questions that deal with impulse. Now, a very good illustration I can also give to you, which I think is very, very important for now, is understanding the concept very well. Let's take it just as the way we have been talking about momentum. So we have two bodies. The first one is having mass of m1, and we have two blocks of equal masses, or whatever you might call it. So we have, or maybe I call it m1, m2 for understanding sake. So let me call this one m2. So let's say now this is moving with a velocity of v1, and this is moving with a velocity of v2. Velocity in this direction, nothing more, potential. So now the initial time of this one initially was time t1. T is t1, and finally it reaches a point of what? Of time t equals to t2. Now the grant, now we have, if force is applied to this particular stuff to push this body. Now what we say now is just we have what we call momentum impulse relation, just like the way we have work energy theory, or work and energy relation. So it's also possible because as I apply a force to this body, we expect this body to start moving and gaining momentum. So we say now, from the knowledge of that, of our conservation of energy, from the knowledge of our work energy theory, we also use that in understanding the rate of change of momentum and impulse. So we call this one impulse momentum equation. Please keep it at the back of your mind. Impulse momentum equation, because a force was applied to this body. When the force was applied to this body was at a particular point in time, this body starts moving. It has gathered momentum. So because it has gathered momentum, we say, just like work energy theory, we say the initial kinetic energy of the body plus the potential energy of that body must always be equal to the final kinetic energy. So in impulse momentum relation, we also use that initial kinetic energy, that's initial momentum of this body. What's the initial momentum of the body? Everybody know m1 v1. From what I have illustrated, momentum is mass and velocity plus, now we say initial kinetic energy of the body plus the work done on the body. So initial momentum of the body plus what? The impacted force of the body. Now the impulse of this body. So the impulse of the body is what? Change in what? Force times. You can say impulse is force times change in time. So we say F times dt. In this case, it's T2 minus T1. I can write it as T2 minus T1 must be equals to the final kinetic energy of the body. I'm using work energy theorem. So this is what I'm reading now. Impulse momentum equation follows the work energy. So the final kinetic energy of the body, the final momentum of the body in this case is now M2. Then we have a V2. So this particular equation I have set here, let me highlight, is called the impulse momentum equation. So which you need to keep at the back of your mind as well. For some cases, directly you can apply the formula to get what answer. Impulse momentum equation. So these are different cases, like I said, which you need to keep at the back of their mind, because it is very important for you to know this, that the change in momentum is called impulse, and it is only applicable when a force is applied to the body, which make the body to get momentum. And in so doing, you can always change what different cases. So guys, before we move to the next one, I hope you guys are following and I hope you are getting there. And if you have any issues with understanding the concept, that's why you can download the video and watch over and over again. So all formulas I have derived, like I do say, formulas are very important in physics because directly you can apply them to solve a lot of questions without wasting time. So I said momentum change is called impulse. The amount of force that has been imparted on the second body. So impulse is change in momentum, and it is F times change in time. So which can be constant and which can be variable. When it is variable, that is when we what? Whenever anything is variable in physics, we integrate. So that is what we do. It will be given in form of equation. So that is how you get to know them. So they are kind of very simple to understand when you see them in question. So another thing is you can also have it at the back of your mind. Whenever you plot a graph of what? F against time, force over time, as in force over time. Whenever you plot the graph of force over time, it's going to give you what there, but the area under the curve for force time graph is always equals to what? Is equals to change in momentum. So always keep that at the back of your mind, because area of force times time is what? Is change in momentum, which we call what? Impulse. So keep that at the back of your mind. And for illustration's sake, we can quickly draw that. Let me pick my pen and do that before we move to the next slide. So we are talking about when you have area, because most of the question in UTM ask you about area under the curve. So if you put force against time, and you're going to have a curve, something like that. So the area under the curve, which is the shaded area here, from initial time, from here time T1 to time T2, you can see there's a change in time. So this area under the curve, the shaded portion, in that case is called change in momentum, which you also call impulse. So area under the force time graph is called a change in momentum. So always keep that at the back of your mind. So area under force time graph is called impulse or change in momentum. So with in sequence to that, the next thing we're going to talk about here is the cases of mass additions on bodies, still on the conservation of momentum. And in doing that, that means I'm going to prepare a new slide to understand the next concept, which we call concept of mass addition of moving bodies. So about the concept of mass addition of moving bodies, we are going to talk about the major case you have studied before, which I'm very sure about, talking about addition of masses. That is a situation whereby we talk about bodies stick together after collision. Stick together. When bodies stick together in junior classes, in class 9 and class 10, most of you've actually studied about this before, so that we can have a space. So in class 9 or in junior classes, you have studied that when you have, let's say there is a grand frame, just like what I did the other time. So on the ground, you have two block system. The block of the first one is M1 is now attached to another one of mass M2. Sorry, diagram not drawn to stay. I am rushing, and the bodies stick together. The mass of M1 is moving with a velocity of V1, and we talk about initial and final velocity. Now these bodies are stick together. So because they are stick together, we can keep it at the back of our mind. Like I said, they are moving together, sticked. Now because they are stick together, we can say initial and final momentum. Initial, before collision, we have M1 V1 must be equals to, you can see, mass addition, because they are after collision, M1 plus M2 with the final velocity of what? I'll call that one VF. So which is basically what you guys you've studied before. So you can make final velocity solve your formula. That is M1 V1 over M1 plus M2, which is another important formula when bodies stick together. That is addition of masses when they are stick together. Another thing I think you need to be careful about, especially for UTME students, is the case whereby the direction of question is telling you that this now they are moving together in the same direction. Then you can see masses are added together. Now, in case they after, when I talk more about head-on collision, you are going to understand this very well, which I'm still going to take at a particular point in time in the video. We're going to talk about head-on collision and restitution. You are going to understand the concept well. Now, for now, what I want you to keep in mind is that body moving stick together and moving in the same direction, mass addition is always what we do. We add the masses together. That is just the concept we need to keep in mind. Now, another case which I think I can also quickly bring here is a situation whereby there is a ground as well. Again, there is a ground. On the ground, we have a block of mass, initially M1, moving with a velocity of V1. So now here we have, let's say, we have another body of mass M2. It's also moving with a velocity, you can see, of V2. Now, in this case now, after this body collide with this body, you know, both of them will now have what? A final velocity, which we call Vf. So we know that initial momentum must always be equal to final momentum. I told you momentum is denoted by rho or P. That's the way we write it in physics. So initial momentum here, from what you can see, you don't need to waste your time. Initially, this is the body before this was fired into it. So initial momentum M1 V1. Then plus, you can see this body is coming to meet this one. M2 V2 must be equal to the final moment. After each of them enter into each other, you have the case of what? The body is stick together after entering M1 plus M2 mass addition. I hope you can see this. Then into what? Into the V final. So this is another important formula, which is like saying V final is equals to M1 V1 plus M2 V2 over M1 plus M2, which I believe is a famous formula you've all learned in SS1 about when two bodies collide, the total momentum before collision is equal to that. Before collision, this is the initial momentum, M1 V1 plus M2 V2. Then after collision, the body are now sticking together. We add the masses together. So the only concept I'm talking about here is addition of masses, which you need to keep at the back of your mind. So keep that very well at the back of your mind. And you can also have another situation whereby the bodies are not sticking together. Maybe they are moving separately, and it is in this case you can say M1 V1 plus M2 V2, or you say initial, let's say initial as U, M1 U1 M2 U2 is equals to M1 V1 plus M2 V2. So this is another situation which can also occur in this type of relationship. All these I believe you have studied before, and directly all these formulas here can be used directly to solve a lot of questions when we get to the illustration side. So you keep them at the back of your mind for now. Like I said, this should not give us issues because most of this concept has been taught in our junior classes. So guys, keep them at the back of your mind. Then we move to the last cases we have talked about in the previous slide. Let's check. Oh, block moving over block. block moving over block, another block, block moving over another block, block moving over another block cases. That should be it. So that should be, this is nothing. I think that was the typo error from the student preparing the slide. So the case of block moving over block cases, we can quickly illustrate that. I think that is for a little bit of some of you doing JUPEB and IGMB. That is very important for you to understand. So the cases, we can just take a simple case of a block moving over block. Block moving over block cases. Now, let's say we have diagram is just the issue. To draw a better diagram is not always easy. So let's say we have a block like an L shape, as you can see. So we have a block. Initial block is resting on ground as usual. My block will always rest on ground. So let's say the block is resting on the ground. So, and because the block is on the ground, it's having initial mass of, so this is the ground I'm showing, my dear student. So this is the ground. The block is having a mass of M1. So there's a small block on this particular L-shaped block, which I call is having a mass M2. So which has initial velocity of V. Let me call it V. So now we say, as this block moves, if a force is applied to this, the gain momentum, the block will start moving and it will slide up, which everybody knows. And because of that, we need to understand the ground. This particular block, this first block, is at rest. Just for understanding's sake. Now, because that is at rest, two things must be noted. Now, there is a particular height. This is the height of this block. You know, the block, the big block, is having an height of, let me just call the height H, just for understanding's sake, to a particular. So this will start moving till it gets to this particular point. Let me just show the block M2 now has gathered momentum and move here. So when it gets here, they are going to have a final velocity, which we don't know, according to what you can see here. So using the same conservation of momentum, we can actually treat this type of block moving over block case, which I believe it is for A-level student. For UTM student, you may not concentrate on this, but whether you like it or not, if you are going to do physics in year 1 and 2, you are going to have cases of questions on this type of relationship. Now, because this is as you can see, this is horizontal, and we know we've talked about normal reaction before. Normal reaction is always acting perpendicular to the surface. We know that. So normal reaction will act like this. They will balance out each other. Normal reaction acting between the block and the ground. So because of that, the horizontal, because this is at rest. So the momentum of this one initially is what is 0. So the velocity of the body is 0. M times 0 is what? Is 0. I believe you understand that. So if we go by initial must be equals to final, we can say because all the horizontal forces has been cancelled out as 0. So as the body is moving here, please always keep it at the back of your mind. So what I'm saying now is that at the top of this thing, you know, we have two cases now. We have X direction, and we have when it is moving up, we have what? We have Y direction, which you need to understand. So here, you just need to understand concept very well, because without concept, you won't be able to relate a lot of things. So understanding the concept now, we can now say, now here, the initial momentum here is M2V. Let me call it V1, just for illustration's sake, must be equals to the final momentum. You can say the final momentum, the masses, the body is starting here. You can say this one is not having horizontal momentum initially, but when it reaches the final stage here at top of this one, this body also we have what? We definitely have what? The masses of this one, which is M1, and the masses of this one will now stick together, just like mass variation or mass addition we've talked about. So their final masses will now be equals to M1 plus M2. Then they will now move with what's common velocity, which we call phi, the final velocity, which is what you are looking for. So the concept is one like what we have discussed here, and always keep it at the back of your mind. When a block is placed over another block, the body moves up they stick together at the end of the what movement, and they move with the same what velocity, which can be related by what like this. Now, another important thing you can also keep in mind is that you can also calculate the height, because there are some questions that ask you to calculate the height at which this particular body will reach. Then if you want to calculate the height, you must go with the knowledge of what? The work energy theorem. You know, I'm always saying work energy theorem because that is what we use mostly in physics to get a lot of formulas. Now, using the work energy theorem, I told you initial kinetic energy. You can see initial energy here is our initial kinetic energy. Work energy theorem is always telling you initial kinetic energy plus the work done must be equals to the final kinetic energy. I'm waiting for this to come up. It has come back. So initial kinetic energy is half, everybody know kinetic energy is half mv squared. So we have half m2 v1 squared. Now, you can see the body is moving up. Then here, the body is doing a negative work on the ground, like it is going against gravity. You know, when body is going against gravity, instead of it to be plus, it should be what? Minus. Please, I just want you to understand on this short concept. Then we say the work done here, which is in form of what? That is the potential energy, which you guys know. Potential energy is always mgh. That is m2 gh on the body, which is moving up, must be equals to the final kinetic energy of the two body. Half, you know, the masses are now m1 plus m2 into brackets what? The final velocity per square. So this is the relationship we set. Initial kinetic energy plus the work done. Work done is the potential energy here, because the body is what we can say is doing a negative work against gravity, and the potential energy is mgh, which you guys know very well, must always be equals to this. I hope you understand how we come about. So from this relationship, we can quickly calculate the height to which the body has reached the forward at this particular. So guys, that is that about the first slide, and that is what you need to know. Like I said, the most important thing here about physics is just understanding the formula and how to relate the formula and how to use the formula conceptually, you can say. And that is what I'm trying to do, giving you different cases so that when you come about those cases, it will just be like a direct question which you can just put values. I hope you understand that. So in context and in sequence, we move to the next slide. Well, now the next slide is talking about the mass addition of moving bodies, and we've talked about mass addition of moving. In fact, I don't know there's a slide separately on that, and the pendulum bob, I guess. So let me quickly talk about pendulum. I don't think that one is simple. It's a difficult situation. So everybody know how pendulum bob cases look like. In case of pendulum bob, we can just take a sorry about that, excuse me. So we take a bob that is tied up a ceiling, like what we can see. That's for understanding sake. So let's take the initial mass of this bob. Mass of the bob is m1. So because the mass of the bob is m1, then we say velocity of the bob initially, I will take it as vb. Note that. So let's say a particular mass, another material was fired from here to meet this particular thing. Let's take the mass of this one to be m2 and the velocity of this one to be v1. Please, my v1 does not give you anything, that I'm just taking an initial and final. It's just initial mass and velocity of the first body, initial and final velocity of the second body. So because I'm taking v1, v2 doesn't change anything. Just for you to know, before collision must always be equal to after collision. That is the concept we are learning under this topic. There's nothing more pretentious. So I hope you can understand that, and understand that values of m1, m2 does not change anything. Just for you to understand before collision and after collision cases. So we know this is going to pass through this. It's going to pass through this, and because it's going to pass through this, you can see this is going to pass through, and it will come out. Let me just show you the direction of the ball. So if it was fired. Let's say a bullet was fired. Let's consider this to be a bullet that was fired. Then it will come out here. Permit my diagram. I'm just trying to make out best diagram for you with my hand. It's not always easy to write with mouse. I keep saying that. So we are now saying, now listen guys, now because this is a pendulum curve, you know, as this thing was what fired to this, we can say the initial before the collision, we have initially the momentum is m2 v1. You know, initially must always be equals to, fine, must now be equals to when it was fired. You and I know something. Then the final, what this thing is, the final collision is now, you can say m1 vb plus, you know, this was fired, then it will come out here, then which will now, the final velocity will now be equals to v2. Then we say m2, and the final velocity of the gun or of the bullet that was fired. So initial velocity of the bullet was v1. It was fired to this pendulum board. And you know, from circular motion, we've talked about that a lot of time. Because of from circular motion, this will take a turn. And you can calculate the what? Angular amplitude, which we call alpha, which we have talked about. And if you know what video on that, we can continue to what we can just check out the videos on how to calculate that. But what I want you guys to just know from these cases is very simple. It was when this thing was fired initial, before collision, when it collide with this, yeah, this one has its own mass, has its own velocity of the ball. Then after it penetrates into this, the final velocity of this particular bullet is now at v2, then which was the mass, which is what. So before collision must always be equals to after collision. That is the only concept we have been talking about since human. And about mass additions of moving bodies, I've talked about that, which we've talked about bodies sticking together and different cases. So this is another illustration that gives you details, orientation, and understanding of the concept. Right? When you have initial can be single, and the after collision, the ball collide, you know, you can see this will start moving. Then this that enter this will move with what the final velocity. I hope you understand this concept, and I believe this concept is going to help you in solving a lot of questions in near future. So guys, we move to the next slide. Like I said, we've talked about what was made a slide here in the previous slide. So that is why we don't have much to talk about in this particular slide. So we move to the next concept, wow, which is what we call the head-on collision and the coefficient of restitution. So my dear students, this is also very important for UPEB and IDNB students, as they are going to be testing them. In fact, in the last UPEB question, they just completed UPEB examination. Coefficient of restitution question was asked, which was a simple question anyway. And for those in 100 and 200 levels doing physics, definitely you are going to come across this, and you should pay attention to the concept so that when you have questions on them, it will be very, very simple and easy for you to deal with them. Now, when we talk about head-on collision, to understand that we are talking about collision of bodies along the same line. That is the meaning of that. That is just collision of body. Let me just write, because if I don't write, I won't be able to make up a note. Along the same line. So that is one thing. So we can just take an illustration. We have a ball of mass m1, you know, it's collision and moving with a speed, initial speed of, please permit my diagram, u1. Now, another ball of mass m2, you can see the line of movement is moving with what? Speed of u2, which is what you guys have studied in junior classes. Now, if these two bodies collides, you can see normal reaction react on them. We don't need along the same line. You can see the normal reaction, which is always like that. Now, the body will now start what you can say the body can now, so we now start to gain momentum after collision. So we can say the final velocity of the first one is v1, and the final velocity of the last one is what? v2. So along the same line, you can say here when they collide, they are going to gain some kind of potential energy, which we talked about in the in the other slide, when we talk about work energy theorem, initial kinetic energy for flux potential energy must always be equal to the final kinetic energy. So you always keep that at the back of your mind. So because of the change in conservation of energy, as you can see, body collide, first ball collide with the second ball, come in contact, then they gain velocity and they start moving. So in this, we now define three different types of collisions, which you have to keep in mind. So because of the collision and because of the line of collision of bodies, according to what I have illustrated here, we define three other types of collision, which we now call, the first one we call elastic collision. Elastic collision. The second we call, this is hanging seriously, so permits this to come up. Elastic collision. The second we call partial elastic collision. And the third we call inelastic collision, which I believe in your junior classes you might also have studied, and if not, you just need to listen as I take you through this. Now, when we talk about elastic collision, that means bodies are not sticking together. We've talked about that. So that means the amount of energy is what? What we talk about in physics is what? The energy. Energy is constant. I'll just say energy is constant. There are lots to write about. Energy of the body is constant. So when we say partial or partial elastic collision, we are talking about the loss of energy is what? Energy that is lost. Energy that is lost is always less than the maximum energy of the body. That is the definition we give to a partial elastic collision. Then the third one, which we call inelastic collision, is talking about a case whereby the energy that is lost is what? Is maximum. That is all the energy has been lost. So in order to understand better, I think I can give you a better definition, which I believe every one of you need to understand. So we can just write that for elastic collision, for you to understand better, for elastic collision, we say potential energy. Potential energy gets converted to kinetic energy. So kinetic energy I'll write as Ke. Now for partial elastic collision, we say the potential energy, or let's write it in a better way, some potential energy, some of them has been what? Has been lost. So in that case, when we say some potential energy has been lost, what we are talking about is that the potential energy that has been lost is what? Is less than that of what? The total amount of kinetic energy. So keep that in mind. And the last one, we say the inelastic. In the case of inelastic collision, we say, please keep it in mind, the total potential energy. Total potential energy is lost during collision. So this is just what you need to give for those doing JUPEB and IJMB to keep at the back of your mind. For inelastic collision, the bodies are, you know the meaning of inelastic, the bodies are sticking together. So when bodies are together, all the potential energy has been lost, because all energy, there is no separation between body. That is why potential energy has been lost. No separation between bodies. So keep it at the back of your mind. So keep it at the back of your mind, guys, that when we are talking about bodies that are moving in the same line of collision, those type of bodies or cases bring about three different types of collision, which can be elastic collision, situation whereby the total energy has been converted to kinetic energy. The situation whereby we have partial elastic, in which some potential energy has been lost, and we see the kinetic energy of final is less than the kinetic energy of initial. The final kinetic energy is very, very small to converted to compared to the initial kinetic energy of the body. You can see the body is having M1, U1, plus M2 U2 equals to M1 V1 plus M2 V2. We've talked about that. It can also be M1 U1 plus M2 U2 equals to M1 plus M2 into bracket what? When the body moves together, final velocity. Because when that one occurs, we say we have an inelastic collision, and in such cases, there is no separation between bodies, and the total potential energy has been lost during collision. So the total potential energy has all been lost, and because of that, there's no potential energy, and that is why we don't have also M1 V1 plus M2 V2. Rather, we have M1 plus M2 into bracket the final velocity. So, and that is what brings about your formula, which you have crammed in your junior classes. So, understand this in 3 ways, and in sequence to this, we define another parameter we call coefficient of restitution. Now, the coefficient of restitution is just now in continuation to that, we define what we call coefficient of restitution. Now, in physics, coefficient of restitution is denoted by small letter e. It's just giving us what? The separation velocity. I'll give it in a simple language. Separation velocity divided by approach velocity. This is my own definition, which is good. Approach velocity. So separation velocity divided by approach velocity. Now let's take what we have in front of us here to understand. Now, where is the separation velocity? You can see they started like this, they come together, the potential energy, some will lose potential energy, some will convert all potential energy, some will convert some of the potential energy, and after that you can see this now. So if this occurs, please note this, they are separating. So separation velocity is the final velocity minus initial velocity divided by, excuse me, I want to make a good note. Let's make a note. It's very important to make a note to understand concept very well. The approach velocity, you can see the body starts from here, trying to approach this one. You can see, then they come together in potential energy here. The potential energy here, you can see, before they now convert it to what? Kinetic energy. Some of them will lost everything, and some of them will convert only part of them. So the approach velocity is always the initial velocity of the first ball or first body minus the initial velocity of the second body, which we now say U1 minus U2. Please keep this at the back of your mind. Some people will say relative velocity of separation divided by relative velocity of approach. We are saying the same thing. So any definition you give to your coefficient of restitution is always the final velocity minus what? The initial velocity over the initial velocity, the final velocity of the second body minus initial velocity minus final velocity of the first body over initial velocity of the first body minus the initial velocity of the second body. I hope you understand the language in which I'm talking, which is the physics language I'm using. So I believe you guys understand that. And in that, we now say, fine. We now use that also to define these 3 all types of collision, which I think we also need to keep in mind for objective questions. We say for elastic collision, my dear student, please keep this in mind. For elastic collision, we take a situation whereby we say the coefficient of restitution is equals to 1. Why is it equals to 1? It is very easy to understand. We say elastic collision energy is constant, that is, potential energy has been converted to kinetic energy. So the amount of coefficient of restitution is always equals to 1 for elastic collision. The second case, for partially elastic collision, for partially elastic collision, some of the kinetic energy, some of the potential energy has been lost. So we say the coefficient of restitution lies between 0 and 1. This is the relationship we give to it, please. It's lying between 0 and 1. And for the last case, which we call inelastic, situation whereby bodies in which all potential energy is lost during collision, we say the coefficient of restitution is equals to 0. So because all potential energy has been lost, that means there is no potential energy in the body. There is nothing like what? A restitution. So separation velocity over approach velocity is called coefficient of restitution. So in that sequence, we can bring what? From here, you can see what I have here is just E is equals to V2 minus V1 over U1 minus U2 is the formula you keep at the back of your mind. So from that, if I cross multiply, I can say, therefore, please, you need to keep in mind, because some question will give you in terms of coefficient of restitution. So what you need to keep in mind when you cross multiply from here, we are going to have V2 minus V1 is equals to E open bracket U1 minus U2. So in sequence to that, my dear student, we already know that what from here, the normal relationship that was set in this body is we can call this one system of equation 1. Then we say from the conservation of momentum, we have M1U1 plus M2U2 is equals to M1V1 plus M2V2, which is an equation 2. So solving this simultaneous equation and getting the what? The final velocity of each of them, V1 and V2 from this equation, which most question we ask you, why I help students in getting formulas is because directly they can apply the formula to solve questions. So we can say the final velocity from this equation will give me M1 minus E M2 is just knowing 1, when you know 1, over M1 plus M2 multiplied by everything here multiplied by U1 plus M2 into bracket 1 plus, that should be 1 plus the restitution. This is 1 plus E close bracket over M1 plus M2 multiplied by U2. It's a simple formula you can keep at the back of your mind anytime, any day, any moment. So this is a simple formula for the first velocity, final velocity of the first body. In that, you can also get the final velocity of the second body. And if you do that, to get the final velocity of the second body, you say the final velocity of the second body, which is V2, will now be equals to, you can see it's just changing the parameter. M2, you solve this equation, this is what you're going to get. M2 minus EM1 over M1 plus M2 multiplied by the U2, then you have plus M1, 1 plus restitution, 1 plus restitution over M1 plus M2 multiplied by U2. So questions that I get, because I think most recently somebody gave me a question in the WhatsApp group to solve, which was actually directly from this formula, and I have to explain how I come about it. In fact, that was the major reason why I decided to make collision and conservation of momentum video for understanding sake. So this is how we come about that. In case of question that give you coefficient of restitution and ask you to find the final velocity of the two bodies. So this is how we come about the formula, and this is what you have to at the back of it. So guys, that is all about head-on collision and coefficient of restitution. Important fact is knowing that restitution is equals to 1 for elastic collision. It is between 0 and 1 for partially elastic collision, and it is always 0 for what? Inelastic collision, because potential energy has been lost during the process. So keep this in the back of your mind, and keep the relationship also as well in the back of your mind, so that you can apply them directly in solving questions. So we move to the next one. The next one is what we call oblique collision. Now, when we say oblique collision in physics, what we are trying to talk about is that we can represent collision of the body in what? In 2 dimensions. That is just talking about 2-dimensional collision, 2D collision. So when collision is in 2D, we call it oblique collision. So don't disturb yourself. Somebody else to define oblique collision. These are collision of the body that is moving in 2 dimensions. So now in that, we can just try to give an illustration about bodies that are moving in 2 dimensions. And in doing that, let's see. So like I said, looking into oblique collision, we can consider 2 different cases. Let's just consider a snooker or a billiard ball, anything you call it. So considering a snooker or whatever, let's say we have the first snooker or snooker board. I got not drawn to scale. I just want to, sorry, apologies for that. There's a break in transmission. We have mass of M1. Then we have another one. Please, it can actually come from different positions. So you guys are very good in playing snooker. So let's say that one is moving horizontally. Let me just give an illustration. So that's for the case. Then we have another one. That's for you to get simple illustration for what they call oblique collision. So this is moving with an initial speed of u1, then m2 moving with you can see what I'm trying to do. I want them to meet. That's what I'm trying to do. Moving with that speed, so they collide with each other here. Then, so normal reaction, like I said, we always act between them, which you have studied before, which I think it may not even be important for now. So we have the normal reaction N. So now when they collide, you can see along the line of collision, we can continue to trace that. Just for you to see, we are just trying to analyze motion in 2 dimensions. So there is nothing more pretentious. It is nothing hard. What you study your dynamics is what we are just trying to talk about. So because of that, you can say the first body here, we now move, just trying to give some illustration. This one, follow this path. Want it to be neat. That's why I'm trying to use arrow. Thereby the second body, follow. I need to make this one longer. So those are the issues now with drawing. For me, that is what I want to do. The second body, let me just do that first. Most like this. This is the point where the 2 bodies are colliding. Just for illustration's sake, guys, which the normal reaction is acting between them. So my point of explanation here is that this one will now move with an angle of θ1, which, like I said, is actually what you guys have studied before. So initial speed of the second body is u2. So as the body collide, this now move in this direction. That's why I give a very simple study about this, which we call the snooker. So this one is now moving with initial. Let's say this first one was the one that moved like this. So V1, the first one after colliding move like this. Then the second one after colliding move like this. This is V2. So representing this type of motion or collision in 2-dimensional plane is now what we call oblique collision. So always keep that in mind that this is x-axis. So along the line of this, we can also bring out y-axis so that we know how to resolve sine theta and cos theta. You should know that's where we are doing. So now understanding this, we can say, so along the line, so let's first bring this. I hope students still remember how to resolve components. So we have that. So nothing more pretentious. I think it's very simple. So now the angle between these two, θ1 and θ2, is called angle of divergence, which I believe under light we are still going to talk more about that. So angle of divergence. So that is that. Now keep it at the back of your mind. Now we can now bring different cases and resolving this into different components. So let's start with elastic collision, which is the most important one. Now for elastic collision, now remember that for the elastic collision, coefficient of restitution is 1. So let's just start with the initial. Now let's say we're talking about kinetic energy after the bodies are got lifted together. L potential energy will be converted to kinetic energy. We've talked about that in the previous slide. So if we go by that, we can say initially the kinetic energy of this one is half m1 u1 square. Half mv square is kinetic energy. For those who don't know, plus half m2 u2 square must be equals to half m1 v1 square plus half m2 v2 square. So that's the first one, which is very easy for us to know. It's just like normal. Then another thing we can also set is also understanding that the angle. Now let's resolve this to horizontal. I hope students to remember horizontal is along the line of x. So if I'm resolving this to the horizontal, keep it in mind. It will be what? Cos theta. As in this will be v1 cos theta, this will be v2 cos theta. So keep that at the back of your mind. So using conservation of momentum as well. Initially, this one is traveling at an angle of 90 degrees, so which you know very well, as it is a straight line, so it is not having any angle initially. Look at where it started, no angle initially. So we can say M1U1, this is the momentum before, plus look at the second one. This one is having an angle initially, which you can see. You can see this one is running along x-axis. This one is definitely going to have an angle of theta 2, which is the angle between the second mass and the velocity. So you can say you have a M2 U2 cos theta, you can see, is now equals to, then after collision, two of them is now having different angle. So we have M1 V1 cos theta 1, which is the first one, plus M2 V2 cos theta 2. So that's the second equation, which is also very important for direct solution. Another one, we can also resolve this into what? Into the vertical, that is the y-axis. Very well, everybody know y-axis. Now, doing that one, you know, to be signed, resolving that. And doing that, we need to understand something very well here. In this case, the second body, if this second body is to be resolved, we say M1, you can look at this, guys. Say M1U1 sine theta is equals to, here we have M1 V1 sine theta 1. Then look at this, guys. Here, this is acting upward, this is acting downward. You know what it means. Upward and downward, we subtract, because they are not what you can say. It's going up, this one is coming down. So opposite direction, you know, you have to solve. That is why this is going to change to minus, because I'm resolving everything to this what? To the vertical. So it will be minus M2 V2 sine theta 2. So it's also another direct formula we can keep in mind. So it's just resolving motion, momentum, and collision into two-dimensional system. And if you have done that, that type of what collision is called an oblique collision. So what I've done here, you can look at in the third formula is M1U1 sine theta, because what I did here was I resolved the second component. If we resolve that one, that is 0, because initially we are resolving to the vertical, it's already at the vertical. Please note that. So I resolve that to the vertical, then I have M1 V1 sine theta 1. You can see opposite over hypotenuse. Opposite over hypotenuse is sine theta. Then I told you if I resolve this one here, you can see it will be opposite of this one, because they are in what? In opposite direction. So always keep that in mind. It depends on the nature of the question that we actually tell you on how to resolve into different components. But keep it at the back of that. Most cases you have this type of illustration. If there is another different cases, using the same concept of resolving them into components along the horizontal and the vertical, and be careful about the starting point. Be very, very careful about the starting point, because if you are not careful about the starting point, you are going to make a very big mistake in understanding the concept. So that is that about this, and that is what you need to know when it comes to oblique collision. So illustration and example will give you more details on how to solve, depending on what student actually prepared. So the next one, guys. Next one is a collision with a floor. Now, about collision with a floor, we can also analyze collision with a floor. It's a very simple concept, just more or less like what the oblique collision we've talked about. So now we can talk about in terms of elastic collision. We can talk about partial elastic collision. Or we can talk about inelastic collision. So now looking at this now, let's quickly understand what we call collision with a floor. It's more or less like our light theorem reflection of light. Now, doing that, let me just quickly take a good diagram, which I think I should be able to do this time around. Now, let's say this is a floor. The particle or a snooker ball was actually hit on the ground like that. as it's not capable. Then when it hits the ground, you know, this we are going to have the normal. It will be what? It was incident on this, then it's going to be reflected. That's why I said we are doing more like it's going to be reflected back. So now one thing you need to understand, this was the incident. So we are going to have the normal. I think we can use this. Illustration will give you a lot of understanding on this. So I suggest you watch our practice question separately for every concept. We have practice question of 30 to 40 questions that we solved for students to have a direct way to solve question instead of wasting time. But concept is also very important, especially if you want to explain to another person who doesn't have an idea about the concept. So now, be that as it may, this was incident at an angle of theta. From light, which we are still going to talk about more concepts later, you know, to what angle of incidence is always equals to angle of reflection to reflect back with the same. So we say U, can see oblique collision can also be set here. U, it was incident with U, initial speed is U, final in which the body we bounce up back with what? With a V. And in this case, we can say V is equals to U from knowledge of reflection, which we have studied. And the angle is also the same thing. Here we can also say, another thing you can also say is that we can say reflection angle is the same thing as well. The angle at which this one is what is also moving up. So the angles is also the same thing. So this is the normal. This is the ground, it's a floor. So when we talk about collision on the floor, I think the major thing we need to understand is that in case of elastic collision, we know that, or in case of elastic collision, we know that coefficient of restitution is equals to 1. And because it is equals to 1, we can say V is equals to U. And also I can bring like the angle of divergence, the way this one has diverged, angle of divergence is also equals to what? The angle of reflection. So that's another point you can keep in mind. For direct question's sake, that's the essence of doing this, for you to understand that for inelastic collision, it's a partial elastic collision, it still remains the same. It is always between coefficient of resistivity is always between 0 and 1. This thing is not writing again. Okay, it's back. It's between 0 and 1. So we relate that. Then for this, we say it is always what? Coefficient of restitution, not resistivity, please. It's always equals to 0. So my point here is that when a body collides with the floor, always keep it in mind. Always, for elastic collision, the coefficient of restitution is always equals to 1. And when that happens, incident or the initial speed is always equals to final speed, and the angle of divergence is also equals to what? The total, or you say angle of what we call this is a oblique angle. This angle in which this one is diverging is the same thing as the angle at which it is what? Reflecting. So always keep it in mind that well, theta 1 plus theta 2 or alpha plus theta is always equals to 90. All these are just illustration. We give you more details about what I'm trying to talk about. But in essence, keep it in mind that floor collision is an example of oblique collision in which you can actually set different cases. If I want to go advanced, I can bring other cases whereby the body, I can resolve this one when the body is moving on the horizontal, and you know when it is moving on the vertical, just like what we did in oblique cases. But because of time and other things, the most important thing you need to understand is the solving component of collision in oblique form can also be done to when the body is colliding with the floor, which also follow the same principle. So nothing more pretentious. There's nothing you cannot do on your own. Like I do say, this is just about learning the concept. An application of the concept is very important in problem solving questions, which you can actually get on our Telegram pages and also on our WhatsApp page. So guys, let's move to the last slide, which I think is slide 52. So the last slide as prepared by the students here is a cases of mass variation. Now for cases of mass variation, we are going to look into another very important aspect we call rocket proportion, because that is what is in the syllabus. So that is the only concept I'm going to talk about, rocket proportion. So the rocket proportion of a rocket. Now, in proportion of rocket, for those of you who have watched our simulated video on that on Telegram, we've talked about the application of Newton law of motion also before. And talking about that, let's talk about how this works. When we talk about rocket propulsion, there are some parameters students need to keep at the back of their mind. There's what we call the thrust force, which is the force at which the rocket will be propelled. Now, let me just take an illustration, just a simple illustration. I am not drawing. In fact, I cannot be drawing with mouse. It's kind of very difficult. But for now, I'll just take a simple illustration to explain what I'm trying to say. So you can see even my diagram for now is not even what I'm trying to draw. But for the sake of understanding, I always have to draw. So drawing, I said we have a rocket of mass capital M is fired. Look at this, my rocket self. I just hope it's a good rocket. So it's fired. You can say with what? With an initial speed. So the initial speed of u, taking that is the speed relative to the rocket. Please always keep that in mind. This speed is relative to rocket. So now, because of that, as this is being fired, there's what we call an ejection rate. That is the rate at which this thing is ejecting. Ejection rate, which is denoted as what? R, which is measured in kilogram per second. Let's keep that at the back of your mind. Now, ejection rate, that is the rate at which the rocket is ejecting per second. It's denoted by R and it is measured in what? Kilogram per second. So please keep that at the back of your mind. It's very important. So the mass of what? We said the initial mass of the rocket is M. It is moving with a speed of what? Of V. So it will recoil. You know that just like the application of recoil of an action and reaction are equal and opposite. So like I said there's what we call a thrust force. So we say the thrust on rocket. Thrust on the rocket is always equals to, we say, the ejection rate multiplied by the what? By the speed of the rocket, as you can see. So this is what we call the thrust of the rocket. This thrust simply means the force at which the rocket will be propelled. So keep that at the back of your mind, the force at which rocket is propelled. I hope you are following. Now, my point here is now we need to understand something very important. Two things. I can start deriving how we come about thrust on rocket equals R times U. But because of time, like I said, I'm not going to be talking more about that for now. So keep in mind that the thrust, most questions for the thrust on the rocket, when rocket propulsion is always what? The ejection rate multiplied by the speed of that rocket. Now, also keep it in mind from second law of motion. Second law of motion, which we call F equals to, we've talked about that, F equals to m dv by dt, which I want to use to bring the last formula I'll talk about for today. Hopefully, you remember this m dv by dt, which we talked about, the law of rate of change of momentum. From that, the force on the rocket, which we call the thrust on the rocket, is R times U. So which we call RU is equals to m into bracket dv by dt. I hope you are following. So now here we can now say, if we want to get the final speed, the speed at which the rocket is being recoiled, we can say the final speed, which is V, is what I need here, which I want to make sort of formula. By that, I have to rearrange this particular expression I have here. So if I arrange, I'm going to have in terms of dt divided by, now another thing which I think I need to relate here for you to understand very well is this small letter m, which we call the mass. Now, this small letter m here is also given in terms of what is given as capital letter M minus what? RT. I think it's important to know. This is the total mass of the rocket. So which what is going to what? It's having a mass of M. So you can say ejecting at the rate of what? R in kilogram per seconds, has a thrust of RU. Then we say the mass, the initial mass of this will now be the total mass of the rocket minus its ejection rate, the thrust at which the body is being ejected. So the mass, this small letter mass, this small letter m is now given as, you can always keep in mind, is the mass of the rocket minus the thrust on the rocket. That is the mass at which the rocket they will move. Is ejecting. That is the small letter m. So it's always capital letter M minus the total thrust on the rocket, which we have as m equals r m minus rt. So don't forget that formula also is very, very important. So now we say, it is actually ejecting at a particular point in time. So the mass that is ejected is equals to what the total mass of the rocket minus that of what the rate at which it will be ejecting at a particular point in time. So this formula is also very, very important, especially for advanced students. We are dealing with advanced cases. Now, here rearranging this, now I'm changing this one to m minus rt to be m. Now I'm changing to m minus rt, capital M minus rt must be equals to, it will give me, this is dv over ru. I've only changed m here to m minus rt, then rearrange. So doing that, at a particular point in time, at an instance of time, I'm going to integrate from 0 to a particular point in time, and I'm going to do that also to this. So taking that, integrating both sides, this is a kind of simple work, which I believe you guys can do. So if I integrate this, I'm going to have something like, then I have dv over this one. Dv will give you v. Everybody knows that. And if you have problem with integration, I told you before you start learning physics, watch the basis of calculus, which I have provided in my channel. You have to watch them. Some of you are wondering what is calculus doing in the physics videos. It is important for you to understand all this type of advanced cases which you need. So derivation may not be important. So then finally, I can say this is the same thing as this will give me v. Let me just do it directly. Is equals to negative u log, or let me say natural log of m, capital M minus rt over, this thing is angle, sorry, over capital letter M, which is the formula I want you guys to work. So the speed at which the rocket is moving is given by this formula, which is what you just need. The essence of my derivation and everything is for you to know this particular formula, which is always very important when you are dealing with question on rocket propulsion. So guys, why I need to talk about this and how do I come about that is simple. 1 over something, when you integrate 1 over something, is ln of that thing. So the t will give me t. If I integrate the t, it is t over, so 1 over r m minus rt is natural log of m minus rt. This one is v over ru. So if I do that, cross multiply and rearrange, this is what I'm going to have. So for those of you who actually want to know everything in details, that is the essence of creating this channel, to give knowledge to everybody free of charge. So guys, this is where I'll be stopping. But before that, I think there should be a slide that talks about illustration as usual. But these illustrations are not the most important illustration, because you are still going to be faced with other illustrations like the tough ones, which we are going to provide when we are through with all topics here. They are ready, but we have to make every videos in sequence. We are doing the upload of the remaining part of our dynamics so that you guys have everything that is needed. Whenever you have issues, you can quickly come, recommend for a friend, let them see what they need to know. So now guys, we talk about the illustration slide, and here guys, as usual, I will take you through on how to solve the questions. I may not be solving the question directly for you, just taking you through how to solve the question, and you do the rest on your own. Well guys, now let's take the first one. Thank God this is no calculation. An elastic collision takes place between balls of known masses. Just before the collision, one of the balls moving with a known velocity, okay? With a known velocity, fine. While the other is stationary. Look at the board. So you have to understand English to be able to solve anything. So now, what do I know, guys? So which of the following physical quantity can be determined from the information? So let's start. They have different mass. Let's say the first mass, just for us to understand solution. The first mass, they said balls of known masses. Let's say the first mass to be m1, I'm sorry, and the second mass to be m2. Affirmative. So if this is the case, now we can now go by the momentum of the first one is m1. Let's take the first velocity. m1 v1. The second one is stationary. That means the velocity is 0. So v is equals to 0. You always keep this at the back of your mind. So v is 0. So keep that at the back of your mind. So we say the second one is giving you, you know what it means, plus m2 times 0 must give you the total board masses addition, m1 plus m2 v. So this is just like saying m1 v1 is equal, because it's 0 times any quantity is 0, m1 plus m2 v. So the only parameter we can calculate here is the v, which is simple as m1 v1 over m1 plus m2, which you can see. You can calculate the speed, and if you can get the speed, that means everybody should know if the speed can be gotten. So we can say the total momentum of the body can be what? Can be what? Or the two balls after collision can be getting, because you can get the final speed. So the speed of each of the ball after collision, no, we can't get the speed because the ball are going to move together. So this is wrong. The kinetic energy of each of the ball, no, so far the speed cannot be gotten. Total momentum of the two balls after collision. The total momentum of the two balls after collision, you can see m1 plus m2 into bracket b can be derived, which is what we are talking about. So this is the correct answer to that. Mutual forces exerted by the balls is also very. So guys, that is that. The second one is, I think, a direct question, which I will just take you through as usual. A ball of mass 200 grams traveling with a velocity of 100 collides with another ball of mass 800 grams moving with 50 meters in the same direction. If they stick together, what will be their common velocity? So directly, my dear students, m1 u1, just like that, plus m2 u2, they are moving in the same direction, equals to m1 plus m2 bracket what v. So whereby you substitute the parameter, drop the answer in the comment box, and so on. So guys, that is that about that. I think we have one more last slide. So why I'm adding, I told you, cases of mass addition when bodies are moving in same direction. If they are moving in opposite direction, to be m1 minus m2. Very important, especially for UTM students. Quote me according to what I'm saying. Very, very important. So the last slide is wow. A body of mass 4.2 gram moving with velocity of this due east. It's a stationary body of mass this. If they stick together, you can say, just like what we did in a stationary body. So you can say m1 v1 is equals to m1 plus m2 multiplied by their final stuff. So this is the same thing. You are going to do this and this, then multiply by their final stuff. You are going to. Why am I not adding the other one? Because it's stationary, just like what we did here. You can see. So always keep that at the back of one. So the next one, which is the last question for the slide, a snooker ball X of mass 0.3 kg moving with a velocity 5 meters per hour. It's a stationary ball Y of mass 4.4. Oh wow. Snooker ball of X is a stationary ball of Y. So let's say Y is like this. This is Y, this is X. So now this is moving with 5 meters per second. I'll just give it, I think this is oblique collision. We don't need to waste our time. So now this eats this, just like what we talked about. So we have two components. Just let me just quickly do that. So this will move, we know that very well. So when they eat each other, so they will now move and form something like an angle. X will move like this. That is the direction of X. And then we have, it is moving horizontally. Diagram not drawn to scale. This permits me. A stationary ball of Y. Y is moving at the direction of 2 meters per second. Okay, after collision, this is it's not moving with 2 meters per second. This is 2 meters per second. Then what happened? We are told then the angle was 30. That is oblique collision that we talked about. Sorry, I'm rushing you guys. Then the angle of this one, you don't know after the what? They collide. So the body was stationary initially. So you can see you have to resolve into components. This is X 5 meters per second. The mass of S is then the other one collide with another one of mass of 0. This Y is having mass of 0.4 gram, which I'm not showing. So guys, the question has find the common velocity. Now to get the common velocity of this one, we use our oblique collision, which we have also studied. So let's start the first one in the direction of X direction. Sorry guys, I'm rushing. In X direction, we can say momentum is mv. The first one in x direction, you can see direction of x direction. You can see, let me say x direction. This is when they collide. X is moving in this form. This notes that, and y is moving in this form. Y is going like this. X is, so this is x collide with this. It moves like this, and y is going like that. So in x direction, I can say mass, that is 0.3. The velocity of that, we have v cos theta. Then I have plus 0.4. That is the mass of y, that is stationary, times what's the speed? I think it was given. We're told that the speed is 2 cos theta, or 2 cos, the angle was given 2 cos 30, must be equal to the final heat. That was where's the final heat? 0.3 times 5. Or you say before collision, this is 0.3 times 5 is equals to after collision. That's what I'm doing. Look at 0.3 is the mass of this one, collides with this. This was stationary, that's with plus 0. That's why I'm not adding a 0. And when they have angle, I'm resolving them. You understand, whenever I use cos, you know the line in which I'm resolving to. I'm resolving along the horizontal. 0.3 times, we don't know the speed of this one after collision, it was not given. But for the second one, we are given that what? The most recommended velocity of 2, and the angle of this one was 30. So that's the first equation I will set. Then the second equation will be along the other direction, oblique collision. That is why you need to watch concept. So now doing that one, I don't need to waste time. So you know, I'm talking about sine. So this will be 0.4. Then we have times 2 sine 30 plus okay, because they are not in the same line, like I said in the concept, to be minus 0.3 times v sine theta. Oh, this is hanging and I'm rushing. This sine theta, seriously hanging. This sine theta is not writing at all. V sine theta must be equals to 0. So this is equation 2. So you solve these two equations directly. I have only used the concept of oblique collision, which I've explained in the concept. So solving this directly, you are going to get the answer. You have two equations. You are going to get answer for theta. And when you get answer for theta, you are going to get answer for what? For v, which is the common velocity. So I expect you to drop answers in the comment box. If you have any question related to this, I can help you break it down. You can join our Telegram group and as well as our Facebook page. So guys, see you soon. Don't forget to like and subscribe to the channel. Thank you and God bless.